Welcome to Astronomy Universe, where we explore the universe based on the most reliable scientific evidence. Today, we'll delve into a fascinating physical phenomenon concerning black holes and the possibility of extracting energy from them, an area under active research with promising initial experimental evidence. I am Astronomy Universe, and on this journey, we will focus on verified physical principles and the latest experimental results related to energy interactions with rotating objects, including well-founded scientific speculations about black holes. Could the immense gravitational power of black holes be harnessed to serve the energy needs of the future? Could these energy interactions lead to strange cosmic phenomena we've never witnessed before? And what terrifying scenarios might unfold if a rogue black hole approached our solar system? Let's explore these mysteries together. Black holes, regions of space with extreme gravitational pull where the event horizon marks the point of no return, have long captured human imagination. However, for black holes undergoing rotation, a special region of space surrounding them holds the potential for an incredible energy source, the ergosphere. According to Einstein's theory of general relativity, the rotation of a massive object drags the space-time around it, a phenomenon known as frame dragging. Within the ergosphere of a rotating black hole, this effect becomes incredibly strong, forcing all matter and even space-time itself to move in the direction of the black hole's rotation. In 1969, physicist Roger Penrose proposed a groundbreaking theoretical mechanism known as the Penrose process. He pointed out that a particle entering the ergosphere could decay into two parts. If one part falls into the event horizon, the other part could escape the ergosphere with greater kinetic energy than the initial particle. This increased energy doesn't come from nothing, but is extracted from the rotational energy of the black hole itself, leading to a slight decrease in its angular momentum. This was the first solid theoretical evidence for the possibility of harnessing energy from rotating black holes. Building upon this idea, in 1971, physicist Yakov Zeldovich made another profound prediction. Not only matter particles, but also electromagnetic waves, including light, radio waves, and other forms of radiation, could undergo amplification when interacting with a rotating object, especially a black hole. This phenomenon is known as superradiance. According to the theory, when an electromagnetic wave collides with the ergosphere of a rotating black hole, the frame dragging effect will twist the wave, and when it escapes, its energy will be greater than its initial energy, taking away a small fraction of the black hole's rotational energy. Remarkably, this theory has moved beyond the realm of pure speculation. Recent experiments have provided strong experimental evidence supporting the existence of this phenomenon. Specifically, in 2020, scientists successfully demonstrated the energy amplification of sound waves interacting with a rotating absorbing disk, showing that a rotating object can transfer energy to mechanical waves. More importantly, a recent study conducted an experiment with electromagnetic waves and a specially designed metal cylinder to interact with the electromagnetic field. The results clearly showed that when the cylinder was rotated at a sufficiently high speed, the energy of the interacting electromagnetic waves increased measurably. This experiment provides direct and compelling experimental evidence that a rotating object can amplify electromagnetic waves, a crucial physical prerequisite for ideas related to extracting energy from black holes. This amplification is confirmed to occur through the exchange of angular momentum between the rotating object and the wave. The idea of turning a black hole into a special kind of bomb arises from combining the phenomenon of superradiance with a feedback mechanism. In 1972, physicists proposed that if a black hole, or any rotating object capable of wave amplification, were surrounded by a material capable of efficiently reflecting waves, The waves amplified upon interacting with the ergosphere would be reflected back, continuing to interact with the black hole and undergoing exponential amplification. Imagine an electromagnetic wave amplified by a black hole, or in the experiment, by a rotating cylinder. If this wave encounters a reflective mirror, it will return to interact, extracting more energy from the object's rotation. This repeated process would lead to an exponential buildup of energy, theoretically capable of releasing an enormous amount of energy in an explosion. Recent research has built an experimental model to test this principle on a laboratory scale. They used a rotating metal cylinder surrounded by electromagnetic coils designed to both create a magnetic field interacting with the cylinder and act as a mirror, reflecting electromagnetic waves. The experimental results showed a clear quantitative outcome. When the cylinder reached a sufficiently high rotational speed, the energy of the electromagnetic field within the system increased exponentially. This energy growth corresponds to the instability predicted in theoretical models of black hole bombs, providing strong experimental evidence that a feedback system capable of amplifying energy from a rotating object is entirely feasible in terms of physical principles. This research not only reinforces existing theories, but also opens up promising new avenues for exploration in physics. One potentially groundbreaking hypothesis being investigated is the possibility of harnessing energy from quantum vacuum energy itself through interactions with rotating objects capable of wave amplification. Quantum vacuum, according to quantum mechanics, is not an absolute void, but rather a state filled with virtual particles that constantly appear and disappear. The hypothesis posits that a rotating object with specific wave-amplifying properties could interact with these quantum fluctuations and realize them into tangible energy. This is a promising area of research that could lead to entirely new methods of energy extraction based on the fundamental principles of quantum mechanics and relativity. At the same time, to realize the black hole bomb idea as a useful and controlled energy source, rather than an unwanted explosion, scientists are focusing on finding ways to control the amplification and energy release process. Future research may focus on designing systems capable of regulating the level of feedback, allowing for stable and predictable energy extraction, opening up potential applications in the future, including the possibility of providing enormous energy sources for spacecraft on long voyages of cosmic exploration. From the well-established foundational physical principles, such as the frame-dragging effect caused by the rotation of black holes predicted by general relativity, and the promising experimental evidence of wave amplification by rotating objects in the laboratory, we can draw profound insights about black holes. Firstly, black holes are not merely passive suckers, but complex dynamical systems harboring a potential energy source within their very rotation. The ergosphere is not just a mathematical concept, but a real region in space-time where energy can theoretically be exchanged and extracted. Secondly, the phenomenon of superradiance, although not yet directly observed from black holes, has strong initial experimental evidence on a laboratory scale, showing that the energy of electromagnetic waves can be amplified through interaction with rotating objects. This opens up a promising direction of research into how black holes interact with their surroundings and potentially influence electromagnetic fields in the universe. Finally, the idea of a black hole bomb, while still speculative and requiring significant technological breakthroughs to realize, demonstrates an intriguing potential for harnessing energy from black holes through an amplified feedback mechanism. It is important to emphasize, however, that detonating a black hole in the way often depicted in science fiction currently lacks a solid scientific basis. Nevertheless, these discoveries are opening new horizons in the study of black hole physics and the potential for harnessing this exotic energy source, encouraging us to continue exploring the deepest mysteries of the universe. Please continue to follow Astronomy Universe for the latest discoveries in astrophysics and cosmology. Don't forget to like, share this video, and subscribe to the channel so you don't miss the next scientific exploration journeys. Thank you for joining us.